In the last video, we talked about certain groups, so I shall continue discussing a few more groups. We talked about these groups R plus. The set was R, the operation was addition. Now, can I say that this is also a group R and this is multiplication? Is this a group? Well, first of all, this must be a binary operation, and it is a binary operation. If you take two real numbers, the product is again a real number. But unfortunately, this does not always have inverse. That is, not all elements of R has inverse with respect to this operation. If I take the number 2 in R, we know that its inverse is half. Of course, the identity here is 1. So, inverse of 2 is half, because 2 times half is 1. Inverse of minus 3 is minus 1/3. But what is inverse of 0? You do not have any number such that 0 times that number is equal to 1. You can't have that. 0 times x equal to 1, that is not present. So, this is not a group. However, if I remove 0 from the picture, then it becomes a group. So, people usually call it R star. So, R star is the set of all non-zero real numbers. That indeed is a group under multiplication. And similarly, C star, where this is the set of all non-zero complex numbers, is a group under the operation multiplication, complex multiplication. An important class of groups are the modular groups. So, this is like this. Suppose n is any integer in any natural number. Then I can consider all the numbers of this type, 0, 1, 2, up to n minus 1. That's my set. And the operation, the binary operation, is this, which is addition mod n. So you add two numbers, then you divide the sum by n and take the remainder. For example, if I take, say, I will just call it by its more usual name, Zn. Suppose I take Z4. If I take Z4, that will be 1 to 3. So in Z4, if I try to add 2 and 3, I will do the following. 2 plus 3 is equal to 5, and then divide by 4, and the remainder is 1. So I will say 2 plus 3 equal to 1 modulo 4. That will be a group. It is quite easy to check that it will be a group. Clearly, it's a binary operation. And all that you have to do in order to find its inverse is like this. Suppose I say 3. What is the inverse of 3? You basically want to say it is minus 3, but this minus 3 you must make it into a modulo operation. That is, if I divide minus 3 by 4 and try to take the remainder, then basically what we are doing is like this. So I have got, just imagine the number line 0, minus 1, 1, 2, 3, 4, the entire number line, no modulo thing here, minus 3, minus 4, and your minus 3 lands here. So when I say divide by 4 and take modulo, I mean identify that multiple of 4 which is to the left of minus 3. And in this case, the multiples of 4 are 0, 4, minus 4, minus 8, etc. So minus 4 is the largest multiple of 4, that is less than or equal to minus 3. If you start from that, you have to move one step to come to minus 3. So minus 3 is actually 1 mod 4. So that is the definition of this modulus. So the additive inverse, the inverse of 3 will be 1. And you can easily check that if I write 3 plus 1, then 3 plus 1 is 4, divide 4 by 4, remainder is 0. So 3 plus 1 is 0, which is the identity element. So these modular groups are useful because for every size n, you have a modular group of that size. It's also an abelian group. When we looked at this R plus, we knew that it was a group. Then we asked the question, is this a group R with multiplication? And we saw that no, it's not a group. Certain elements were not having inverse, in particular 0. Throw that out and that then becomes a group. We also saw just now that Zn plus was a group. The question naturally is, if I consider multiplication, modulo n, is that a group? And the answer is no, it is not a group in general because you do not have inverse for certain elements. Let's take this case again, Z4, that was 0, 1, 2, 3. So what will be, well, first let us see what is the operation. Suppose I am trying to do 2 times 3. So when I say 2 times 3, I mean it is, so first form the product, 2 times 3 is 6, divide by 4, take mod and you get 2. So 2 times 3 is actually equal to 2. Now my question is this a group? Well, it's a binary operation, no problem with that. It has got identity element also. 1 is clearly the identity element because multiplication by 1 doesn't change anything. No problem with associativity because it is derived from ordinary multiplication, which is associative. However, inverse is a problem. For example, let's take 2. So if I say some x here is inverse of 2, I will need this 2 times x must be equal to 1. That is 2x must be equal to 1 mod 4. That is obviously not possible because this is even, 4 is even. So you can never get an odd number because this will require you to do the following. So take 2x, which is an even number, divide by 4 and the remainder must be an even number. So this is impossible. So 2 does not have an inverse. In this way, we can see that this cannot really be a group. However, just as in this case, we turned it into a group by throwing away the unnecessary things, here also we can do the same thing. In this case, the modification is this. I will define Zn star to be the set of all members of Zn such that they are relatively prime to n. And now if you take this product, it will become a group. It is not very difficult to see why this will be a group. So I will leave that as an exercise for you to check that why it is a group. So relatively prime to n means the GCD of m and n will be equal to 1. And I think you know about Euclid's algorithm, the way we used to compute GCD back in school in the long division kind way. So from this we can say that if m and n are relatively prime, then you can find integers a and b such that am plus bn is equal to 1. So a and b are integers. Whenever m and n are relatively prime, you can get this thing. And from this, you should be able to conclude that such an m must have a modular, must have an inverse mod n. So I leave it as an exercise. If you can do it, if you can do this, you can write down the solution in the comment. If not, you can say that you cannot understand it. Then I will provide the answer. The topic we are studying is the group theory, which is part of abstract algebra. Now, whenever we think about algebra in our high school context, we think of problems like this. I have a number If I add 5 to it, I get 7. Then what is the number? And we have certain manipulation that we do. So the manipulation that we typically learned is, if you have a plus 5, then you take it on the other side and somehow magically the plus becomes minus. So x is equal to 7 minus 5, and that is equal to 2. So this is just like certain manipulations. Now we can do the similar thing in group, and the setup is like this. Suppose I have a group, I will use G and I will use dot for the product, and eventually we shall just drop this notation. So instead of writing A times B, I will use the more familiar notation AB. So I give you a number of elements in G, so I have give you an element X in G, and just as I had 5 and 7, similarly I will have some elements A and B in G. This is completely abstractly I am writing things down. G could be just any group, and I give you the equation XA is equal to B, and from this I want you to solve for X. What is X for which it will happen? Now I will do the same thing. I will take A on this side. Now what is meant by taking A on this side? By this I mean I will multiply from the right by A inverse. That is important because I need not say whether it is abelian group. So whether I am multiplying from the right or from the left, that matters. So when I multiply both sides from the right by A inverse, I get this. So XA, this entire thing multiplied from the right by A inverse, B A inverse. Now since it is associative, I can put my brackets like this, and A times A inverse by the very definition is identity. I will denote my identity by E. So X times identity. Now what is X times identity? By definition of identity, that is just X. So I am left with X equal to B A inverse. So you see, the rule is as if you take A from to the other side, A just changes to A inverse. And that was what we were doing here. Plus 5, plus was the operation 5, and it became minus 5. So minus 5 was the inverse of this 5. Similarly, A inverse is inverse of A. So the rule that we learned in school still works here, and the proof is just straightforward. Here is another rule that we learned in our school days. Suppose someone gives me 2x equal to 2y, we know we can cancel 2 and we get x equal to y. Now let's see if we can do a similar thing for groups. Again, I will work with a general group, and I am working with elements 2, x and y. In general, I will work with a, x and y in G, and the condition that I am being given is ax equal to ay. Can I cancel a? Well, the answer is yes, you can, and the rationale behind that is you are multiplying from the left by A inverse, because whatever your A is, A inverse will be there. So it is A inverse AX equal to A inverse AY, and regroup thanks to associativity. You see how frequently I am making use of associativity. So that is identity element, that is identity element, identity times X is X, identity times Y is Y, therefore you are left with X equal to Y. And you can easily see that I can do the very same thing if I am starting with XA equal to YA. Then I will be multiplying from the right by A inverse, and again I can do this thing. But remember, you cannot do the following. If it is AX and YA and your multiplication, this binary operation is not abelian, then there is no guarantee that X is equal to Y. In fact, here is another example which is a little less trivial than the last one. Try to come up with a counter example you must use a non-abelian group for which this works. In case you are wondering, for which it fails, that is, for which you have got ax equal to ya, but x is not equal to y. Now, if you are wondering how to go about it, I will just remind you that there is only one non-abelian group that we have seen so far in these lectures, and that is the group involving this triangle. So, we had got 6 elements there. Try to get hold of 3 elements in that group a, x, y, such that ax equal to ya, however, x is not equal to y. Suppose that I have a group and an element a in it. I know that every element in G has an inverse, so A has an inverse, which is A inverse. Now A inverse is again inside G, so this again has an inverse, which will be denoted by this. Is there any relationship between this and this? Now possibly you have already guessed from our everyday examples that this must be A itself. Like if you are working with say R and plus, or say Z plus, and then element is 2, we know that its inverse is minus 2, its inverse is minus of minus 2, and that is 2. Similarly, if you are working with multiplication, say R star and multiplication, you start with 2, its inverse under multiplication is half, and this is 1 by half, and that is 2 again. So it's quite natural to guess that A inverse should be A itself. Is that always true? Well, yes, it is always true. And here is the proof. To prove this, we have to first observe this fact, which is that if I give you any element x, then x inverse is unique. So the same element cannot have more than one inverse. So I have not proved this. I earlier proved that unique existence of the identity element, but this is also a fact that you should try to prove for yourself. If I give you any element x in a group, it has got exactly one inverse. Now I can prove this quite easily. I will just say, I know that A times A inverse is of course A. That's is of course identity. So A inverse is A inverse A is identity. So from this I can see that A itself qualifies to be inverse of A. So if I call this B, then I get BA equal to AB equal to BA equal to identity, and therefore I can say that A is B inverse. And what is this? This is A inverse, B is A inverse and inverse of that. So from this I conclude that A must be equal to A inverse inverse. And I am using the fact that for every element its inverse is unique. Otherwise all that I can say is A is one inverse of A inverse and this is another inverse of A inverse. So I cannot say that they are same, but since every element has got only one inverse and both this and this qualifies to be that inverse, they must be the same.